All right, so hi everyone, we're going to get started. So for today's lecture for CS25, very pleasure to have Denny Zhou from Google DeepMind here to give a talk on large language model reasoning. And so Denny founded the reasoning team at Google Brain, which is now part of Google DeepMind. His group is renowned for pioneering chain of thought prompting and self-consistency, as well as developing the mathematical foundations of in-context learning and chain of thought reasoning. His team also created core capabilities that powered Gemini's reasoning capabilities. Further, Denny co-founded the Conference on Language Modeling, or COLM, and served as general chair for the 2024 conference. I'll let Denny take it from here.
Yeah, I'm glad to see many of you guys have already believed LLMs can reason. Actually, you may wonder what's my answer for this question. Yeah, to me, actually, I don't know. That really depends on the definition of reasoning. So for my talk today, we have a very specific definition about reasoning. So I know there are many debates about if LLMs can reason. I never joined those debates because without a definition on reasoning, I have no idea about those things. But for LLM reasoning, and we particularly mean that intermediate tokens between input and output, that's called reasoning, or intermediate steps. So this idea actually is not very new. Even in 2017, DeepMind already published a paper how to use intermediate tokens to solve math problems. So at that time, I think the community was quite hyped about AlphaGo, AlphaZero. But this paper is really groundbreaking paper. If you haven't read that paper before, I strongly encourage you to look at that paper. They introduced natural language to solve math problems. However, in the literature at that time, I think everyone else just used a symbolic approach or search. So actually, this idea actually is also very common for neurosymbolic literature. In neurosymbolic literature, actually, it's very common to use intermediate process to solve some reasoning problems. Here's an example about how to use LLM reasoning. When I founded the reasoning team in Google Brain, I created this task. So it's called last letter concatenation. I used this task as a motivating example. At that time, one could use transform models to solve this task. So what's the output when concatenating the last letter of each word of artificial intelligence? So if there's no reasoning process, you will say, okay, the answer is LE. If there's a reasoning process, the model would output, say, the last letter of artificial is L, the last letter of intelligence is E, concatenating L and E leads to SLE or something like that. So the highlighted text here is called reasoning. That's what I particularly mean here about reasoning. So if you are familiar with program synthesis or neurosymbolic reasoning, you wouldn't be surprised about this task design. Of course, you can imagine that I tried other options. For example, I didn't see the first letter. The reason is that I tried first letter, and all language models can solve that problem quite well, because there are so many initials on the web, and the model has already learned how to concatenate first letters. Then I switched to last letters, and all models failed. I know many people say, oh yeah, this is so natural, right? We need intermediate steps, just like humans. I know in the current days, you may see LLMs are very similar to humans. But for us as researchers, we should always keep in mind LLMs are just probability models. They are not humans. And if you always keep this in mind, it will be better for you to understand a lot of new techniques. So why intermediate tokens or reasoning matters? Okay, we have theoretical work. I actually collaborated with Professor Denny Zhou in Stanford and his students. So for any problems solvable by Boolean circuits of size t, constant size transformers can solve it by generating OT intermediate tokens. It's a very powerful result. So the size here means the number of logic gates. So for example, if you use a GPU clusters, that would be tens of millions gates, right? Even the billions, trillions, yeah. If we directly generate final answers, either require a huge depth or cannot solve at all. That's how we understand reasoning from a theoretical perspective. In the later of this lecture, I will come back to this theoretical argument. There's a common belief about LLM reasoning, and pre-trained LLMs cannot reason without further prompting engineering, like COT prompting or fine-tuning. In the current days, everyone talk about IO fine-tuning, right? Is that true? Do everyone agree that? Agree that? Okay. So I believe it's wrong. Yeah. It's very wrong. Yeah. So pre-trained LLMs are ready to reason, and all we need is decoding, just about decoding process. Yeah. No matter how fancy those techniques looks like in the current days. So here's an example here. If I have 3 apples, my dad has 2 more apples than me, and how many apples do we have in total? If you have any pre-trained models like Llama, DeepSeek, or Chengwen or something, and I didn't try those models, okay. If you have any pre-trained models, you can type this question in the pre-trained model and see what happened. Probably it's very likely you see answer like 5 apples. Of course, the answer is wrong here, okay. This is called gradient decoding. You will say, okay, yeah, you're right, right? For pre-trained models, there's no reasoning, right? The problem is about decoding, because we use gradient decoding by default. If you look at the second candidates, if you look at because you have a big vocabulary size, right? And you can look at the second candidate for the first token, and probably we start from I, and we'll see what happened. We'll just then continue the decoding process. We see, okay, I have 3 apples, and my dad has 2 more apples than me, so he has 5 apples, and 3 plus 5 equals 8. It's perfect, right? We just need to look for more candidates. That's amazing. And there's another choice, and the third candidate for the first token is we. We see what happened here. We have 8 apples in total. Yeah, that's somehow is also correct. And probably from the fourth candidate will be you. We will continue decoding. We see what happened here. Again, yeah, this you can clearly see a chain of thought in this response, and the final answer is correct. And this is the 5th candidate for the first token, and the answer is 5 is wrong. Okay, yeah. You can see that actually the reasoning path is already in the output space. And in particular here, for the second response and the fourth response, they are based on chain of thought reasoning. The problem is how to select the best response, right? If we just look at the examples here, you may see, okay, we can by output length. If the model has some thinkings, and the output length will be longer because it contains reasoning tokens. And actually, we have a better idea to select the response, and by its answer confidence. Confidence means because the model is just a probability model, we can look the probability of the token in prediction. A very interesting thing is that for the response with chain of thought reasoning, the answer token has way higher confidence. For this example, actually for the token 8, the model's confidence is nearly 98%. You can imagine that's huge, right? Because we have huge vocabulary size. So usually for each token, the probability is nearly 0. So this process is called a chain of thought decoding. So basically, it consists of 2 steps. Step 1, we just go beyond grid decoding by checking more generation candidates. And in the second step, we choose candidates which have the highest confidence on the final answer. Chain of thought decoding is a very simple approach. But still, it needs some programming work. And I heard in the current days, the people just want to use a natural language, right? No one write code. Of course, you guys are exceptional. And we have to say, okay, can we reshape the model's output distribution so that thoughtful responses naturally rank first? If the chain of thought response is ranked first, and then the graded decoding can naturally find it, right? So now we can look at the chain of thought prompting. If you know chain of thought prompting, now you can see why it works. Chain of thought prompting is a very simple approach. So given this problem, and you probably use another similar problems as an example, and put that before your question. And then the model will magically follow the style, reasoning style, and generate a step-by-step solution. Yeah, now you can see that why chain of thought prompting works, because it changes the output distribution to push the original chain of thought solutions in the output space to the top position. Even there's a simpler approach, it's called a less single by step. That's another amazing work in reasoning. When that paper came out, and I thought it was a joke. How possible? Yeah. And at that time, the Google Brain team built a model called COLM. And I tried less step by step in our PALM model because of course, I know how PALM was built. It's definitely not related to this magic trick. And then I found it works on PALM. I was so shocked. So this paper really inspired me a lot on reasoning research. Those prompting approach, are really simple, and prompting really works. But we can see there's also some pitfalls. So like COT prompting, right? It needs task-specific examples. To to me, I don't feel comfortable about that. If I have questions to ask someone, if I know similar problems, then I can solve it by myself, right? Why should I ask other people? And for the other approach, it's called let's think step by step. It's generic, okay? You don't have to find similar examples. You just say, let's think step by step, and then the magic will come out. Unfortunately, it performs much worse than few shot prompting. And yeah, I just mentioned of that. Okay, yeah, both approach looks well, right? Even for let's think step by step, it's also well, right? If I ask somebody a question, then I have to follow with let's think step by step. Otherwise, they couldn't think anymore, right? That's not expected. So how to fix it? So there's a popular approach called supervised fine-tuning. So for this approach, and the idea actually is very simple. We can collect a set of problems and their step-by-step solutions from human annotators. And then we maximize the likelihood of human solutions. Maximum likelihood actually for LM's training, predict negative token, it's just maximize likelihood. Yeah. And after that, we can apply the model everywhere. So, I listed DeepMind paper in 2017. I mentioned that paper at the very beginning. Yeah, they exactly did something like that. They collected a set of math word problems and also human annotated step-by-step solutions. And then they trained a sequence-to-sequence model to solve math problems. In 2021, and OpenAI actually further extended that approach, built a much larger data set called GSM8K, grad school math problems. And then they used those data sets to fine-tune GPT-3 models. So here, let me give an example how it works. Okay, you can just put a problem here. Like for example, at the beginning, I said, okay, we can do loss letter concatenation. And you can put this example here, the problem and the answer, okay? And the other one is the city math problem, how many apples you can put there. And then use that as a training data to fine-tune your model. And then you can test the model with a new question. So how many R's in strawberry? Probably you know why I particularly chose this problem here, because in social media, many people believe that it's a good question to test if AGI has come or not. Yeah. Yeah, and SFT is really generic approach. Once you train the model, you can apply anywhere, right? And if that can solve reasoning, my talk is done here, right? We don't have to talk more, right? Just collect more examples from those brilliant minds in Stanford, right? We can train the model and it's done. But actually, it doesn't generalize well. And we realized this issue in 2021, in the summer. We found it didn't work well on reasoning. What we could do? Scaling. To get more data to train the model and see how it works. Yeah, it's a lesson here is, don't scale blindly. Once the paradigm is wrong, no matter how to scale, it doesn't work. So, how to fix the generalization failure from SFT? Let's look at the SFT procedure here, right? Just 2 steps. So where's the mistake? the mistake part actually from human. If you don't know that before, you'll be surprised, right? If human analytics are wrong, and how scale AI can make money. And actually, one of my team members invented AI fine-tuning. Actually, when he told me, and the response generated by machines could even better for training than human data. I was really surprised at the very beginning, yeah. So first attempt is called self-improve. Yeah, exactly, just change that. Okay, instead of collecting data from humans, we can just let a model generate data. So collect a set of problems, and also then let your model generate step-by-step solutions. And then, again, maximize the likelihood of correct answers. Like math problems, you may know the final answer, right? You know the ground truth answer, but you don't have step-by-step solutions. Okay, let a model generate step-by-step solutions. And then you can just choose answer to decide which response to be used. If the answer is correct from the solution, then choose that. Otherwise, reject. It's called reject sampling. And then you can use this data set to fine-tune your model. Okay, exactly as you have done in the SFT, the only difference, the data is from your model, is not from humans. And this approach actually was proposed by Eric, right? And Tony, and also Noah, yeah. The paper is called STAR. Yeah, the STAR approach is a really amazing paper. So actually, in the STAR paper, actually, when they proposed the approach, actually, they considered use that to save cost, labeling cost, because human labeling are really expensive. But in the current days, we understand this approach from different perspectives. Okay, once the response are generated or training data generated by the model, and the model can be self-improved, right? And after the model improved, and then we can collect data again, that means we can repeat this process. Repeat. And then this approach is then just the same as the AI fine-tuning approach in the current days. I put a paper here, and I think it's a paper by researchers in ByteDance, published in January 2024. I think this is the earliest academia publication I have noticed about AI fine-tuning. Even the paper title is called Reasoning with Reinforced Fine-Tuning. Yeah. I think after OpenAI 01 got popular, and then everyone began to realize fine-tuning in the public. Yeah, I believe multiple institutions independently discovered this idea, such a simple idea. Yeah, but it works really well. Of course, yes. If you after seeing this AI fine-tuning process, and we need verifier in this training loop, the verifier can tell us which response is correct because we know the final answer. We just need to use that to select the step-by-step reasoning path. So a reliable verifier is the most crucial in RL fine-tuning, not the RL algorithms. I know in the country, so many people talk about different algorithms, and so many tons of variants of PPO or reinforce. If anyone found some algorithms are significantly better than another one, please let me know. Probably I missed something. Yeah, I really like what Richard Sutton said here. Verification, the key to AI. It's an article title by Richard Sutton in 2001. Okay, now a very interesting question is, why generated from the model instead of from humans? That's a really interesting question, right? It's not about saving cost. It's about performance. Does anyone have an idea here? Yeah.
Is it consistency in chain of thought structure versus in humans? There's wrong variation in how different people might approach problems.
About consistency, okay. Yeah.
Distribution is closer to it's easier to draw.
The distribution is
closer. The model is closer to what you do train, so it's easier to train the model.
Yeah, excellent. Yeah. Thanks. So, this is related to first principle in machine learning. Directly optimize what we want. I don't know if anyone still remembers some machine learning stuff here. Of course, you guys should remember that, yeah. So, if we want to build a model for reasoning, right, or just in general about generating something interesting, right, we need to optimize the metric of measuring generation quality. Those metrics could be very different, right? For example, if for solving math problems, we would care about the correctness, if the answer is correct or not. If for machine translation, you would optimize BLEU score, or just about a metric to measure the quality of the generations. Okay. Once you have a metric, all we need is to compute gradients of the metric and do backpropagation. Yeah. So mathematically, we can write this formula, right? We need a function R to measure the response quality given the problem, and also your model parameter, theta. Okay. Yeah. Of course, you can see R is a reward, or R is your classification accuracy, or R is your BLEU score. Well, no matter, you can define any R you want. That's your target, right? And then compute the gradient. Since the model is a probabilistic model, we need to maximize the expected value of the metric. So how to do it? We need to sampling to compute the expectation. That's why you get a policy gradient. Yeah, that's how it works. There's no, if you understand all the mathematical principle here, there's no magic. I know some people would like to talk about something in a more magical way. For example, how to incentivize your model to think, incentivize your model to reason. I don't use those words. I just use standard machine learning words. Define your metric, compute a gradient, and do backpropagation. That's all. Yeah. Of course, yeah. Once you find your paradigm works well, we need to scale your approach. Not a problem is what to scale. Okay. And the interesting is that for this IR fine-tuning approach, we scale the output length or scale the length of COT. And you probably also scale the model depth, right? Because from our theoretical analysis, as long as your COT is long enough, the model can solve nearly every computable problems. That's amazing. You don't have to scale your model size. You just need a minimal constant size transform models, and that's fine. So actually, if you look at the literature, and people realized R fine-tuning is better than SFT in the very early days. But it's harder to notice that we need to scale the COT length. That's even more non-trivial to realize. Yeah, I would like to mention the beauty of LM reasoning. Human-like reasoning process emerged from token-to-token prediction rather than relying on exhaustive search as in classic AI. Yeah. I also have fun quote here by Kasparov after losing to Deep Blue in 1997, and say, Deep Blue was only intelligent the way your programmable alarm clock is intelligent. Actually, I agree with him. But LM reasoning is different. Right? We don't do any explicit search. And the search is irrelevant here. And before my talk, in the hallway, and told me she quoted my my tweet about search is irrelevant. And wow, I said, I'm very happy to know that. Actually, I used the quote and to say search still is useful. Actually, I want to give an example here about why LM reasoning is so different from classical AI here. In December 2024, and Google released a model called Gemini 2.0 thinking mode. Of course, 2.5 Pro is much more powerful. Okay, I use that model is for a particular reason. So in December 2024, after model release, I tried a math problem just to ensure this problem is not in our training set. Okay, because I use a number 2025 for the next year. Now it's for this year. Okay, using the numbers from 1 to 10 to make 2025, and using each number once and the primary operations plus and the multiplication. Okay, of course, one can write a Python program, do exhaustive search, and get results, right? Let's look at the thinking process on the right panel, generated from the model. Actually, for Gemini models, you can check the thinking process, raw thinking process. It's very interesting to look at. Okay, let's see how the model did the thinking, right? It's not by search. You can see that it is at the very beginning, the model said, okay, this is a relatively large number. Right? Suggesting multiplication will be heavily involved. Right? That's just like a human thinking, right? And wow, even I see, okay, it's worth noting that 2025 is 45 squared and 45 times 45. Actually, when I made this question, even I didn't realize that. That's huge hint here. And I say, okay, so the target is large, and I started thinking about how to get large intermediate products use multiplication, and see blah blah, and that's M for products that get us closer to the square root of 2024, which is 45. You see that? And after, actually, I made a cutoff here. The thinking is very, very long. That's why we did long COT in the IR fine-tuning. And you can find an answer after thinking. The model showed the final answer, right? They exactly follow the thinking process. You see, that's a breakdown it. Okay, first part and 10 times 4 plus 5 equal to 40 plus 5 equal 45. And the second part is also again 45 and then 45 times 45 to get to 2025. That's amazing, right? We don't need any search. I don't know if anyone read another paper related to chain of thought prompting. It's called a tree of thought prompting. Anyone read that paper? Great, yeah. In that paper, actually, there's a very interesting example. It's game 24. This problem is way harder than game 24. In tree of thought prompting, they combine search with prompting to solve game 24. But now you don't need that at all, right? The model can solve game 24 just by natural language. I see that this is how IL training is so powerful. It's amazing. And again, I would like to cite Richard Sutton here. You see in the beta lesson, right? The core idea here, okay, building our discoveries only makes it harder to see how the discovery process can be done. Yeah, that's, I think Richard Sutton wrote the beta lesson after he joined Google DeepMind and he saw the success of AlphaGo and AlphaZero. And he said, okay, only two processes are really scalable. One is learning, the other is search. And, but here, I would like to see, I only emphasize one thing, learning is scalable. We just need learning, yeah. And yeah, for RL fine-tuning, okay, yeah. And the big advantage is that it generalizes so well, but for automatically verifiable tasks, because we need a verifier in the loop. There's no way to put a human in the loop there. And of course, not all tasks are automatically verifiable. Right? Can anyone give examples of non-verifiable tasks? Yeah.
Creative writing.
Right, yes, creative writing. Yeah, great example. Yeah. So, yeah, that's the big restrictions for RL fine-tuning at this point. And also many people are really interested in creating RL algorithms to improve the approach. I really want to see we spend more time to think about, how to solve those non-verifiable tasks. For real problems, actually are really non-verifiable, like creative writing, even like a coding, right? And also, so people say, okay, coding problem will be solved by AI in a few years. And I think it would be very challenging to be solved, right? I know actually they will talk about programming, they only talk about competitive programming. Competitive programming is not like our daily programming work, right? So we write code, we care about your design, your readability, right? Yeah, how to collaborate with other people, not just give a final answer. Yeah. Yeah, I have talked about all those ideas. Actually, at the very beginning, I talked about COT decoding. Okay, actually, the reason path is already in the output space, and all we need to do is about decoding to reshape the output distribution such that the grid decoding is founded. Okay, and then I talk about channel sort of prompting or lessons by step, which can reshape the output distribution, and then SFT, and then RL fine-tuning. RL fine-tuning is so powerful, but we still have a chance to improve those processes. Basically, I want to talk about two key ideas. One is aggregation, the other is about retrieval. And we have seen that LM reasoning is really powerful, right? But any decoding issue in the paradigm of generating reasoning tokens and then final answers, right? It seems so natural, right? Given the problem and generating intermediate tokens and then final answer. Does anyone see any problem in this process? Any problem? Yeah.
Is the design of the model is just designed to predict next token. The challenge is the way it predicts next token. That's what creates a situation where the outcome will not be aligned to the expected outcome.
Yeah, great. Yeah. Yeah, the model is originally designed just for predicting next tokens. Yeah. So, yeah, thanks. So, yeah, we need to always keep in mind here that LMs are probabilistic models. They are not humans. What does that mean mathematically? Let's think about what LM does in decoding, right? Given the problem, and generate reasoning, and then final answer. And then the response found by graded decoding. What does graded decoding means? Argmax the probability, right? However, for us, right, we need to argmax the final answer. Choose the answer with the maximum probability, right? Choose the most confident answer. So they are not aligned, right? There's such a simple high school conditional probability math here, but it's really useful for us to understand the decoding process. And we can, let's fix it, right? We just need one step further, okay. If we generate reasoning paths, we should sum over all reasoning paths to find the probability of the final answer. In terms of machine learning, it's called marginalization. Just sum over all, because all the reasoning paths actually essentially are just latent variables. And of course, if we first start machine learning, and then we know actually the sum can be computed by sampling. And then once you get this idea, and then you say, okay, that's exactly the motivation underlying our another popular approach is called self-consistency. So generate multiple response by random sampling, and then choose the answer that appears most frequently. So let me show a simple example here. For this math problem, and you could sample the response many times. For the first response, you will get, say, $18. And for the second one, you will get $26. And again, you will get $18, right? And then we'll look at the final answer, right? And then choose the most frequent one, right? That's exactly the process implementing marginalization in probability. We don't look at the reasoning path, which only choose the most frequent answer, not most frequent reasoning path. That's the trick. That's called marginalization empirically. And if you apply this approach, you can see a huge improvement. It's really surprising. I know in the candidates you have to, you may think, okay, if you want to get a huge improvement, you probably need to spend a lot of time to build a sophisticated math formulations. We don't have to. So for GSMK problems, we can see that, right? Even for fine-tuned GPT-3 models, they used, they got actually 33%, and then OpenAI used verifier to get accuracy 55%, and use PAM model plus COT, we get accuracy 58%. That's amazing. That's match the performance from the verifier. And then, however, the most surprising thing is after applying self-consistency, the accuracy jumped to 75%. The relative improvement is nearly 50%. And use Palm 2, we even get an accuracy 92%. And of course, one may say, okay, yeah, that's for Palm models. Use, the model for several years. Sounds like 10 years ago. Because in the current days, every year just like 1 decade. The whole field is moving so fast. Actually, if you look at the 01 model, I forgot when OpenAI released 01 model, probably October last year, right? Yeah, and actually they also showed the results by aggregation. See that consensus at 64 use, and then we still see great improvement by aggregation or self-consistency. Yeah. Yes, great point. Of course, yes, by using self-consistency and use more samples will be more expensive, right? Use more tokens. And people see that's kind of inference time scaling. Yeah. There are so many ways for inference time scaling. If you use a longer SOT, that's also increase inference time. So actually, when some people told to me about inference time scaling, really, I don't know what they exactly means unless they can explicitly see what's scaled. Yeah. And the self-consistency is definitely a way to scale up. Yeah. And also, self-consistency is naturally self-calibrated. Higher consistency indicates higher accuracy. It's for GSMK benchmark. Actually, when the self-consistency is more than 80%, the accuracy is nearly 100%. So I know some people care about uncertainty or confidence in prediction, and they can just simply try sampling multiple times. And I have two short questions here. So to make sure everyone got the really key ideas in self-consistency, I hope you know how to, you really found a lot of fun using this simple idea. So the first question is, okay, when the LM outputs a direct answer without intermediate steps, will you still sample several times and then choose the most common answer? Will you? Does anyone have an answer here? If the model just directly generates final answer, what do we do? Yeah, go ahead.
This is like you can just get probabilities you don't have to.
Exactly. Yes. Exactly. Just like exactly what we did in the classical machine learning, right? We'll have use logistic regression to get a py given x. We just need to maximize the probability there. That's why we couldn't see self-consistency in the old machine learning literature. It's unnecessary. It's only useful for LM reasoning. That's why we see it here. After we have reasoning, and then we need self-consistency. Yeah. And the second question is change self-consistency by letting LMs generate multiple responses instead of sampling multiple times and then choosing the most common answer. Does this make sense? And you can see, you just tell model, generate 5 answers instead of sample 5 times. Right? Yeah. That's actually, we can try that. And again, for everything, we just need to follow the machine learning principle. Actually, this principle is called max marginal inference. Yeah. You just need to choose the final answer with the maximum probability. That's all we need to know. You don't have to think about any fancy things about LLMs. Don't have to compare with humans, you know. Math is all we need here. And one can naturally, of course, self-consistent has a problem. You see the unique answer, right? You check the frequency of the unique answer. And for general problems, it's hard to see the answer will be by a single token. And for example, for this problem, you will see all the answers are different. Okay, in this case, we have a extension about self-consistency. It's called universal self-consistency. And for this problem here, you can see the second response is the most common one, Japan, China, and India, because all these three countries are in all other answers, right? And we just need to let LLMs choose the most consistent response. Okay, I've talked about how to use aggregation to improve reasoning. The other way is about retrieval. So I know there's a lot of debate about LLM reasoning. So people say, okay, LLMs may not just do retrieval instead of reasoning. I know many people, I saw that debates in the social media. Actually, to me, it's always hard to differentiate retrieval and reasoning. And when I'm area chairs or senior area chairs for all the conference almost every year, and we always have to talk about the novelty of each paper. And actually, it's similar to the debate is retrieval or reasoning, right? Yeah.
Similar to the concept of self-consistency. I sort of try an experiment with trying different models to run in parallel. And then running parallel, they may have literally like running GPT-4, running the same concurrently with running Gemini 2.5. I run like 4 different models in parallel for the same question. And then at the end, just having like a verifier. So sum up and find the most consistent result.
Yes. Yes, if you generate response from different models, that will be more like the model assembling approach with many models and combined results, like a random forest. Yes, yeah. The mathematical principle is not exactly the same as self-consistency, but the implementation are the same. Yes, yeah. Great point. Yeah. Actually, again, I'm not interested in the debate about retrieval or reasoning. And for people working, actually, I work in industry, I really just care about performance. So to me, just do retrieval plus reasoning. Why should do the debate, right? Yeah. So in 2024, we have a paper about analogical reasoning. So I can just use this small example to show why retrieval is important in reasoning. Okay. So for this problem, see what's the area of the square with the 4 vertices, blah blah. And okay, the highlighted text is added by me, and say okay, it's a prompt. Okay, recall a related problem and then solve this one. So at that moment, I tried GPT 3.5 and also our own model, and they failed solving this problem. After adding the prompt of recording related problems, and the model can solve it. Right? Let's see what happened here. After tell the model to record related problems, and the model did find a related problem. Related problem doesn't mean the same problem. It's indeed just a related problem. You can see the related problem here is finding the distance between 2 points on a coordinate plane. And there's a formula there. And then the model, oh yeah, now I know how to compute the distance and then how to compute the area. It's just a small case to show how retrieval is important in reasoning. Here's another example called step back for the physical problems. And before solving this problem, we just let the model, we just give few short examples to show the model. Okay, before solving this problem, you can make a step back to consider more abstract problem, get the principle, and then solve it. Right. That's how retrieval works for reasoning. And I think now everyone knows deep research. Deep research is exactly the same idea here, right? So we have a Gemini deep research and also OpenAI deep research. And one of OpenAI's deep research lead was my intern, and after his PhD, and he joined OpenAI, and he invented deep research. Yeah. And you see that how the deep research works, because they can find a similar problem or knowledge to solve the problem. Yeah, the basic idea is very simple. Yeah, now I can give a summary here. Actually, forget about those debate if LMs can reason or not. For LMs, reasoning is always better than no reasoning. And finetuning is better than SFT. Aggregating multiple answers is better than one answer. Of course, that will be more costly. And retrieval plus reasoning is better than reasoning only. And yeah, that's the end of my talk. And for the next breakthroughs, I really want to see, okay, how to solve the task beyond unique verifiable answers and in the candidates. And I also want to see how people build real applications instead of just solving benchmarks. I think all benchmarks will be saturated soon. Yeah. And I know, all you guys are very passionate about AGI or build LMs. I would like to quote Richard Feynman here. The truth always turns out to be simpler than you thought. And I think that's particularly true for LM research. And I saw so many academic papers that always try complicated many things. So that's why I just kept my talk as simple as possible. I think actually it's indeed simple. That's it. Yeah. Thank you.
Thanks, Danny, for the very insightful as well as interesting talk. So now we'll be taking questions. We have some questions online from Slido and Zoom, but also in person. So we can maybe start with some in-person questions.
Hi, thank you for the talk. So earlier on in the lecture, you talked about confidence, and like a common way to do this is like just taking the average log probabilities of output token sequences. Yeah. So like my question is, do you think there are better ways to do this? And also, is this a good indicator for hallucinations?
Oh, for the first slide, when I talk about confidence, just not aggregation, just the probability for next token prediction. Just a conditional probability for the generation. Yeah. Mm-hmm. You can just look the log props from the model and see, and you can see the probability. Yeah. Yeah.
And like, do you think this is a good indicator for hallucinations?
Yeah, same so. Yeah. From our empirical observation. Yeah. And we can see after reasoning pass, there's a huge jump on confidence for the final answer. Yeah.
Thank you.
Hello. Earlier you mentioned that, for example, Richard Sutton said that it's scaling learning and search, and your opinion's more like scaling learning is all you need. I'd just like to expand more on that and
why you believe that search is not as necessary.
That's why I used that example. And actually, okay. So actually, I should make it more concrete. When you build models, you don't have to keep search in mind. But after the model is built, and you can use search as a tool, as a special case of tool use. Like retrieval sort prompting, they can just integrate symbolic search with the model. Yeah. So, but for reasoning research, I just care about the fundamental abilities. Yeah. For example, if you want to solve this problem, the model could be motivated to write a Python program to solve those problems by search. But for the reasoning process, we don't need to search. It's just, how to say it? Of course, we can always search everything. Right? That's why if you use a search to solve any problems, you can get a higher accuracy. And I don't know, that really depends on what you want. Intelligence or just by search. Yeah.
Hi, thank you for the talk. You mentioned in the case where there's no reasoning that it's not necessary to sample because you can simply look at the logits. But wouldn't sampling converge on a different distribution in the case, for example, where the most likely next token leads to a diffuse distribution for the following token and the different paths spread out? Whereas if you were to sample and a less likely token were to lead to a sharper distribution, you could actually have a more likely path of tokens there. So wouldn't these two methods fundamentally differ?
Good question. Yeah. The problem is actually we still don't know how the distributions are reshaped during the training stage. It's very unclear there. Yeah. So it's, to me, it's very hard to answer this question. But we still don't have good explanation how those distributions are reshaped for the final distribution. Yeah.
Thank you.
Hi, thank you for the talk. So how do you differentiate reasoning and answer? Like, do you need to extract that number from the tokens, from the final strings, the output string? What if the answer can be like a program? Then how to differentiate the reasoning and the answer?
Yeah, great question. Yeah, if the answer is a program and will be harder to extract, So when people use AI or fine-tuning, and that's why you just see those guys are talk math problems or competitive programming problems. Yeah. So I think for the general case, you have to write a very careful parser for the final answer. Yeah.
I see. And also, what if the problem is very challenging, so such that actually the lower confidence answer might be the correct answer? Because
possible, yeah.
Yes. Yeah. Then how can I use the self-consistency method?
Self-consistency is not perfect.
I see.
It's perfect, everything is done, right? Yeah, not perfect.
All right. Okay. Thank you.
So considering that, conversations that AGI is coming, like from 2 to 5 years from now, how, and basically if we, if it's true, then let's say 90% of jobs automated. What skills do you, develop in kids to give them a shot to survive in the future that is coming?
That's a big question. Who said AGI will come in 5 years?
I mean, there's like AI 2027, right, by Daniel Kukutayo. Like there are lots of conversations in the AI community that giving like the timeline of like 2 to 5 years.
I was in iClear last year. There was a workshop, and I remember one audience asked me a question in the panelist. And she said, "Okay, and AI is moving so fast, the field, And what would be the most scary thing in the next few years?" And I remember some people did talk about the risk of AI, but my answer is, to me, most scary thing is AI winter comes back. And then I lost my job. Actually, I saw many restrictions for the kind of approach. So I actually, I know many people like the chatbots, OEM sort of things. I really want to see real killer applications from the kind of AI research. I don't know if anyone really needs those AI stuff or not, or just for fun. Yeah, I'm not quite sure about that. I know actually the AI models is really good for programming. Yeah, can be a good assistant for coding. And that's all I know about that. Yeah. We should be fine.
Okay, I think we're out of time. But thanks everybody for your great questions, and thanks again to Denny for the great talk.